looks like that the recording is in progress. So can you see the screen now?
Yeah, we can see. Yeah.
Okay, thank you then. So yeah, my name is Elias Hassani. I'm instructor in Saskatchewan Polytechnic, teaching cybersecurity, and also I'm a PhD student working on post-quantum cryptography in the University of Saskatchewan. So today we're going to talk about the FIPS 203 or ML-KEM. So first of all, this kind of conversation been around for quite a long time. So that especially it dates back to 1994, that the Shor's algorithm that we're going to discuss a bit about it shortly later was introduced, and then people realized that so quantum threat is quite imminent. So of course we didn't have much power to build such quantum computers, but recent advancement made it even much more possible. And we are very optimistic that quantum capables of performing Shor's algorithm in larger scales might be possible. Some people might say within like 5 years, some might say 10 years, but eventually it looks to be inevitable. So we have to be ready for this shift. And classical computers, of course, been around for a long time, and we didn't have any issue with the algorithm that we use. But now we're going to see how quantum computers can break those paradigms. So you might think about it like if quantum computers are still not in a scale or at a scale that can break the algorithm that we are using today, why we are so worried about it right now? And the answer for this question is that you can actually, an adversary can capture the packets, let's say by using Wireshark or by using Burp Suite, and they can decrypt them later. For example, they can capture your password, or might say like, I'm not worried about it because I'm going to change my password. But you should be worried because there are some information that you cannot really change it. Like your date of birth is always your date of birth, or your social security number or social insurance number. These numbers are attached to your identity, so you have to protect it for always. It's not just a question of today. Now I'm gonna derive it here, like so you better understand like what's going on and why we are worried about the power of quantum computers. If just this allows me to do that, just one moment. I bring the pen here. Yeah, okay. So if we classify the cryptography algorithm that we've been using, I put them into two categories. One of them, I put them to be classical ciphers, and the other category, I put them into the modern ciphers. When I say modern cipher, I'm referring to everything after 1970s. So 1970s onward, we're talking about modern, and classical is everything before that. In classical categories, we have, for example, substitution ciphers, and we have another category that is, for example, the substitution and transpositional ciphers. But now when it comes to modern ciphers that I talk about after 1970s, I put them in two categories. I put them into symmetrical ciphers, symmetrical. And the other category that I'm going to put here is asymmetrical. So symmetrical ciphers, again, can be in two categories. One of these categories is going to be stream ciphers, and the other category is block ciphers. Stream ciphers, for example, you have seen Trivium. I'm just going to give a bit of background for those who are a bit new to this field. And we have, for example, Salsa. We have Cha-Cha. And in the block cipher, for example, we have algorithm like this or triple this or DES that is a bit older and that's broken already. Or we have AES that is much more popular. And we have a lot of other categories too, but just for the sake of simplicity, let's introduce it like that. And in the asymmetrical categories, we have algorithm like RSA, and we have discrete log problem or DLP problems, and ECC that is elliptic curve cryptography. So when I talk about quantum computers and their power, I'm mainly concerned about the asymmetrical ciphers. So this type of ciphers that we've been using for exchanging the keys and digital signatures on the internet. And also somewhat I am concerned about AES that we are using today extensively everywhere. So when it comes to the asymmetrical ciphers like RSA, for example, the security of our RSA relies on the multiplication of two prime numbers. Like if I multiply two prime numbers and I tell you what are the factors, then it becomes a hard problem. Of course, if that number is a small, let's say I tell you what are the, I'm talking about RSA here. What if I tell you a number like 21? And ask you what are the prime factors of 21. So this is a very easy problem. You can quickly say 7 by 3 is 21. So that is easy. Now, what if I increase this number to very large magnitudes? For example, I tell you a number that is 200 digits long. Let's say a number like 9, here, 6, 2, 5, 3, 0. And I continue this for 200 digits. Like let's say the last number is 7. Now, how can you tell me what are the prime factors for this? Actually, even your computers, the best computer in the world, I mean, the best classical computer will suffer to solve this problem. And that's believed to be taking us billions of years to solve such problems. And that's why we rely the internet security on such problems. But by the Shor's algorithm that I'm going to show you quite shortly, with the Shor's algorithm, we can solve this type of problem within hours. But of course, we need large scale quantum computers. I mean, we need quantum computers that has, let's say, 100,000 qubits or maybe even millions of qubits. So we are still quite far from that, but we don't know really when exactly that might happen. But if you consider the pattern in the past, like when the classical computer also scaled, you see that we had a quite fast expansion. So, and the same trend can happen for quantum computers. So that's why we believe that this type of algorithm or this type of quantum computers will be capable very large, very soon. So yeah, any question that you have so far before I move on? If you have question, just I stop like this so you can ask it before I move on. So the way that Shor's algorithm solves such problems, or you can raise the hand too, and then I'll respond to that. And the way that quantum computers actually can solve this with the Shor's algorithm is by finding the period of the numbers here, and that's by using an algorithm that is called quantum Fourier transform. That you can read more about it. It's very interesting how they can find the period and they can find the prime factors of a number. Okay, I'm not going to delete here. So I talked about like how Shor's algorithm, and that is not exactly about the structure of it, but Shor's algorithm is capable of solving such problems. But the other type of algorithm that we should be worried about is Grover's algorithm, as you can see listed here. So Grover's algorithm is very interesting, and it was introduced by at 1996. So if you have an unsorted database, let's say this is my database, and I have some names with the phone number stored on it, and this database is unsorted, which means that it's not alphabetically sorted here. Let's say I have Alice, I have Zach, I have Bob here, and I have Adam here, for example. And now here I have their phone numbers. Now, if I tell you what is the phone number of Bob, you have to go through this database one row at a time until you find Bob, and then you can say what is the phone number until you get here. So here's, of course, is a very small database or database that we have only 4 rows. But imagine that you have a very huge database that you have 2 to the power of 128 rows. Now this becomes very, very hard problems, even for your best classical computers. That's going to take again for ages. But Shor's algorithm actually can solve such problems in the square root of the time that it takes for the classical computers, which means that if for a classical computer it takes to 2 to the power of 128, for your quantum computer it's going to take 2 to 128, the square root of that. That becomes 2 to 64. And we know that 2 to 64 actually is not secure anymore, and the classical computer even can find such keys within the space that we have. So if you are using, let's say, AES with 128 keys, quantum computers, for them, it would be equivalent to 2 to 64, so that is not secure anymore. But if you are using AES with the key size of 256, this will be 2 to 256, and then a square root of that, and that becomes 2 to 128, and that is still considered secure, so we don't have any issue. So Grover's algorithm doesn't make the AES obsolete. Instead, we have to try to increase our key size. So if you are using key size of 128 for your AES, you have to increase that to 256. But Shor's algorithm make our asymmetric ciphers like RSA, Diffie-Hellman, and elliptic curve, all of them obsolete. So we cannot use them anymore. Any question? Okay. Now we have two categories of algorithm that I wanted, two categories of solution, better to put it, that we can solve this problem with. One of them is post-quantum cryptography, and the other is called quantum cryptography. So post-quantum cryptography means like developing algorithm or designing algorithms that are based on the classical computers, but they are resistant against the power of quantum computers. So when I talk about post-quantum algorithms or post-quantum cryptography, I'm not talking about using quantum computers for designing, but I'm just talking about the classical computer for the design. But on the other hand, quantum cryptography is using quantum information concepts for securing the conversation. For example, I can use fiber optics here for transferring, for not fiber optics, I mean like, for example, the photons. That of course can be transferred with fiber optics too. Photons for transferring the keys from the sender to the receiver. And they have some properties, these photons. For example, if Alice is sending the photon to Bob, then if an adversary tries to measure that, we know that the quantum state will collapse, which means that the receiver, who is Bob, will realize that someone intercepted the channel, so they know that the channel is compromised. But of course, quantum key distribution needs a specific infrastructure, so that's going to cost us money. And also considering that we are not using that much fiber optics still too in a lot of places, and we need a specific sender and receiver and quantum detectors. Photon detectors. That is a solution that people are working on it actively. But the cheapest or the cheaper solution and more prominent solution is to use post-quantum cryptography that needs already concluded the set of algorithm that we have to use. Any question? Okay, so the interesting thing is that we can use the hybrid approach. By hybrid, I don't mean like to combine the post-quantum cryptography and quantum cryptography, but I mean to use classical ciphers with post-quantum ciphers and make my communication safe. Let me show you a bit of like simplified approach here. So let's say you are using elliptic curve Diffie-Hellman for key distribution. What you can do, you can also use ML-KEM that I'm going to talk about it today. And now you can combine these two together. Like let's say here we combine them, we do concatenation of both of them. We put them together and now we send them as concatenated. And now if there is any issue with the classical computer, if the classical computers are, the algorithms that are based on classical computers are broken, we know that ML-KEM is still secure. So our channel is still secure and the keys are protected. So is it clear? That's exactly how your browser is doing this today too. And all the browsers today support this type of hybrid approach. In post-quantum cryptography, we have 5 classes that are active. They are under active research right now. We have code-based cryptography, we have multivariate-based cryptography, lattice-based cryptography, hash-based signature, and isogeny-based signatures. But the ones that are more attractive right now are lattice-based cryptography, and we have 2 classes of algorithms. One of them is ML-KEM, also aka Crystal-Kyber. And the other one is called MLDSA, or module learning with error digital signature algorithm. And this is called dilithium also. So today I'll focus on ML-KEM, but maybe I'll do another session later to talk about the dilithium as well. But of course, dilithium is used for digital signatures and ML-KEM is used for key encapsulation that we're going to see what it means. So here I have a table that just shows you the summary of the categories that we have. For example, code-based algorithms are based on the syndrome decoding problem, and multivariate based are based on the multivariate quadratic problem, or lattice that we know is based on the shortest vector problem or learning with error. I'm going to talk about this shortly today. And hash based is to use the hash algorithm that we have today. So we say instead of using and inventing a new algorithm for the digital signature, why we're not using, let's say, SHA-3 family that we know they are already secure against quantum computers too. And we have isogeny based that is also based on finding and mapping between the supersingular elliptic curves. That don't worry about them. We're gonna focus again on this category and the lattice space, and we see how they work. But what is a lattice? A lattice is irregular repeating patterns of points that extend through the space. As you can see in this figure that I provided here, there are repeating points in the 2D space here. And you see that they keep repeating in a regular interval. And now I can have 2 bases in this lattice. Let's say here V1 and also V2. This is my base. And I can get to any other point on this space or on this lattice space by just combining these 2 vectors. For example, if I want to get to point 1 and 2, I can just write V1 plus 2V2, and that's going to get me to 1 and 2. Or if I want to get to point 1 and 1, that is right here, I just need to combine them V1 plus V2. If I want to get to this point here, I have to do twice the size of V1 minus the size of V2, and we get to this point here. So I think it's clear now. You know what is a lattice, and we're going to see how we can use that. So let's first talk about the closest vector problem. I'm going to read the statement first, and then we're going to discuss about it. So it says, given a lattice L, an arbitrary target vector, find the lattice point that is geographically close to T. So again, I get back to my previous figure. So if I give you a target point on this lattice, let's say my target point is right here. This is my target vector. Now, if I tell you find the closest vector to this vector, you can easily say, okay, this is right here. That is a point on lattice. Yeah, sorry, the vectors are not straight, but you got the idea. And now if I tell you my target vector is here, you know that the closest vector to that is right from here to here. So this is called the closest vector problem. And now you might say, but this is an easy problem. How come we're going to use this problem for securing our information? And the reason is that, of course, we're not working in 2 dimensions. The figure that I'm showing you here has only 2 dimensions. What if we are working in 500 dimension? Then you can see that it becomes a very hard problem. Besides this, we have 2 types of vector or bases. We have good bases and we have bad bases. But let me explain you the difference here. So say good basis that we're going to use as our secret key is a set of basis vector that are short and nearly perpendicular or orthogonal to each other. When you view a lattice through a good basis, finding the closest point becomes computationally easy. So if I have 2 vectors that are perpendicular to each other, which means that they almost create a 90 degrees angle with each other, then it becomes easy problem to find any other point in this lattice. Let me get back here. You see in this example that I showed you before, V1 and V2 are short vectors, and also they are not exactly 90 degrees, but they are very close to 90 degrees. What if I choose 2 vectors actually that are now far from each other and they are almost parallel to each other? Now that becomes a bad basis. Now let me get back to my definition one more time. So now say bad basis, this is a set of basis vectors that are very long, highly skewed, and almost parallel to each other. When you view the exact same set of lattice points through a bad basic, finding the closest point becomes computationally hard. So if I go a bit further to show you this a bit more clear. Now you see here, U1 and U2 here are bad bases. You see they are very long and they have a very small angle that they create with each other. So now if I give you these 2 bad bases and I give you a target point, let's say my target is right here. Right here. And this is my target vector. Now I tell you like combine U1 and U2 to get to this U3, for example, or UT, that is my target. This becomes a very hard problem. Again, I'm not in just 2 dimension. I am working in 500 dimension. So finding that becomes a very, very huge problem. And even quantum computers cannot solve that problem within within time that is feasible. I think now it should be clear for you what is the closest vector problem. Here, I'm not talking about shortest vector. I'm still talking about the closest vector. Any question? Okay. I assume that that was clear. Now I'm going to talk about the shortest vector problem, or SVP. So if I give you 2 vectors, let's say again here, like U1 and U2, now I can tell you what is the shortest vector in this lattice. I'm not talking about the closest vector to a target. This time I don't have a target point, but I tell you what is the shortest vector in this lattice by combining U1 and U2. Now this becomes also a very hard problem, especially if your basis vector are very long and skewed, as you can see, and also they are not creating 90 degrees angle. They are creating angle close to 0. So these are the 2 fundamental problems that we are using in Crystal-Kyber. Either we are giving you 2 base vectors, U1 and U2, and I ask you to find the shortest vector in this lattice by combining these 2, or I give you U1 and U2 and I give you a target vector And I tell you how can I get to target vector by combining U1 and U2. Both of these are hard problems that can be used for Crystal-Kyber. Okay, I already talked about this. And this is also, I talked about it already. So this is the document that we're gonna talk about it today. That again, I provided the link for you too. And this been published in August 13, 2024. And this is called Module Lattice-Based Key Encapsulation Mechanism. But first of all, what is key encapsulation mechanism? So if I have Alice and Bob, and Alice and Bob try to, let's say I can't get back here again one more time to show you the concept, and then we talk about it more. So if I have two parties here, let's say Alice and Bob, and both of them are talking to each other here, and we are using, let's say, AES as our encryption algorithm. So this is the message that Alice provides, and this is the key, and this is the ciphertext. And on the Bob side, the same, because Bob needs to receive the message, the ciphertext. Let's say here is the internet, and here we have the ciphertext. I call it C. And here I have again AES. I have the key, and Bob received the message. But how Alice and Bob gonna transfer the key right now? Because they have to use the same key. Again, we can ask someone to do this for us, and that's gonna be, of course, non-functional, as we are talking to lots of people at the same time. So one way is to use RSA, for example, or use Diffie-Hellman. But we just talked about it, that those algorithms are going to be broken by Shor's algorithm. So we have to use ML-KEM or Crystal-Kyber for making sure that the keys is protected and encapsulated while we transfer it from Alice to Bob. That's the underlying problem that we try to solve right now. Okay, now I go forward. Okay. So here we have three categories of that you can choose from for ML-KEM. You have ML-KEM 512, we have ML-KEM 768, and also we have ML-KEM 1024. If you want baseline security, when I say baseline security, I'm just talking about, let's say, IoT security, because you don't have a lot of space to, or you have some information that are not highly confidential, you can use the ML-KEM 512. If you have intermediate security, which means that you want to do a trade-off between the security and performance, you use ML-KEM 768. And if you need maximum security, like let's say you have highly confidential information, you have to use ML-KEM 1024. But what does it mean when I tell you ML-KEM 512 right now? I'm going to use this pen again. So we're talking about ML-KEM 512. So in ML-KEM 512, first of all, K is equals to 2, which means that the module rank, so the lattice rank, or the number of polynomials is 2, which means that we are using a matrix, we call this matrix A, of the size of 2 by 2. So this is a 2 by 2 matrix. And I'm going to discuss this later, how to create this A and what is important to create this A. So here we have 4 polynomials here. And now we have n, that is the degree of polynomials, which means that each of these polynomials are of degree 256. For example, we have, let's say, A1, x255, plus A2, x254, and we continue this until A255 and x0. So you see here, the degree of polynomial is starting from 0 to 255. So the total degree is 256. So in total, the dimension of the lat is going to be k multiplied by n, that is 512. And all the coefficients here, A1, A2, and A255, all of them are going to be a number between 0 to 3328. That's it. Now you can imagine that if we are using 768, only the size of the matrix going to change. Like instead of 2 by 2, it's going to be 3 by 3. I'm going to show you a table that summarizes everything here. So yeah. So the secret is of algorithm, what you should keep secure now. You have to keep secure the decapsulation key. From now on, whenever I told you decapsulation key, you can imagine that I'm talking about this secret key or private key. This is my private key. And also the shared secret, the key that we are using for AES, I call it KAB. And also the randomness that we need to use, because we're going to use random number generators that we're going to see shortly. They also have to be secret. Of course, if they know the seed for the random function, then the security is compromised. And also the algorithm itself or the mathematical structure is now secure, but you have to make sure that your design is also secure as well. For example, your hardware is secure against timing attacks or against any type of hardware attacks. So those are, of course, things to always consider. So these two algorithm or class of algorithm that we used before, they are going to be vulnerable and we should not use them. Again, key establishment through integer factorization and key establishment using discrete log. So those are the broken algorithm by quantum computers, so we're not using them. And try to stop using them. Of course, right now still we are using them, but in a hybrid approach. Okay. There are some acronyms in the documentation. Of course, I'm not going to walk through all of them, and you don't need to do that too. There are two of them that are very important for me. Again, one of them is N, that shows me again the degree of the polynomials. That's going to be 256. And Q, that is just a prime integer, that is 3329. So we do everything modulo 3329. So that makes sense because if we are doing modulo 3329, our number going to be between 0 to 3328. Okay. And this table summarizes all the parameters that you need to choose. Again, N is the degree of polynomials. Q is the modulo that we are using for the coefficients. K is the size of the matrix that you are using. You see for 512 is a matrix of 2 by 2. For 768 is a matrix of 3 by 3. For 1024 is a matrix of 4 by 4. And we have two parameters that are called eta 1 and eta 2 right here, eta 1 and eta 2. These are also used for the error. I talk about it, why we need error terms, and also for the secret keys. So these are like central binomial distribution that we're going to talk about it. And du and dv are called compression parameters. These are compression. Basically, these are helpful for us to decrease the size of the ciphertext and the key and etc. So we want to compress our algorithm. And if you look at the size of the ciphertext and the size of the keys, encapsulation key for the ML-KEM 512 is 800 bytes. The encapsulation key is 1632 bytes. Ciphertext is 768 bytes. And the shared secret key is 32 bytes. Here I just explain whatever I just walk you through. For example, again, eta 1 and eta 2 are the noise distribution parameters that we're going to generate number between -3 and 3, or we're going to generate number between -2 and 2. And du and dv again are for compression. We do the compression to 10 bits and compression to 4 bits, but we'll discuss it later. And here I took this from Kyber PyPy website. So you see the benchmark. Actually, you can see this is very fast. So for example, for ML-KEM 512, the key generation takes us 1.96 millisecond, which is very nice. So you can generate 511.30 key per second. Encapsulation takes 2.92 millisecond, and decapsulation takes 4.2 millisecond. So you can see that it's actually very fast algorithm. So it wouldn't add much delay to your communication if you use that. So here I did a comparison to show you the difference between the classical algorithm that we are using and the modern ciphers. So here we have RSA 3072, or we have elliptic curve, Diffie-Hellman, or we have ML-KEM 768. Of course, these two are not quantum safe, but this is quantum safe. ML-KEM is quantum safe. The speed of RSA is slow. The speed of elliptic curve Diffie-Hellman is very fast, and ML-KEM is actually extremely fast. The only issue with ML-KEM is the size of the public key. You see here the public key size is 1,184 bytes, so it's almost 1.18 kilobytes. But for RSA is 384 bytes, but for elliptic curve Diffie-Hellman is 32 bytes, which is much smaller. But you can see, although it is 1,184 bytes, it still is going to fit within one single standard internet packet that has the size of 1.5 kilobytes. So there's no problem for transformation, but of course it's going to be a bit like taking the memory, and it's going to be a bit of a space issue, or the packet sizes that we are sending going to be bigger. So this picture, again, from the documentation shows you the whole process. So if Alice is sending a message to Bob, so first of all, we have a key generation function. Key generation gonna generates for us two keys, decapsulation key or private key, and encapsulation key or public key. Public key is used by Bob to generate the ciphertext and generate the shared secret key. And Alice will use the ciphertext with the decapsulation key to generate the shared key. Now K and K prime are equal, so both of them have the key for using AES. Any question? So you can see the overall algorithm is not difficult. It's pretty straightforward. We have Alice that generates two keys. Bob used the public key, and Alice will use the private key for getting the shared key. I don't have note here. So now it's very interesting, this part. If I told you about a matrix that is called A, so if I have a matrix that is called A here, this is my secret vector, and this is the error term that I'm using. And finally, Alice is getting something that is called B. This is the public key. This is the public key. And this is the private key. And this is just an error term, error vector. I call it error vector. And A is just a matrix with the size of K by K. Now it's obviously, you can understand if I'm using ML-KEM 512, the size of A is going to be 2 by 2. The size multiplied by S, the size of S is going to be 2 by 1. A vector the size of 2 by 1, plus the error terms that is going to be also 2 by 1. And my public key is going to be also with the size of 2 by 1. And A is just a matrix of, again, polynomials. That's it. I mean, you got it all really if you understood so far what's going on. So we just multiply A by C, my matrix A by secret vector. We add an error term to it, and we get the public key. So you see, like the problem that we are using here, or the type of problem that we are using here, is called learning with error. The reason is that if I don't add this error term here, I face an issue. Let me explain to you what is the issue. Let's say I just have a matrix A, I multiply it by S, and I get the B, that is my public key. But you can see that here we can easily find the secret key. How we find the S by Gaussian elimination, right? So if you use Gaussian elimination, you can find S. So that is not good. That's not the hard problem. That's actually a very easy problem. Instead, we have to add a little bit of error to this multiplication. Now the Gaussian elimination is not going to work anymore for finding the secret key. So we're not using integers here. You see, I could create a matrix A just by integers. But that's going to be a slow process because that needs a very large matrix. Let's say a matrix of the size of 512 by 512, which is not good. Instead of using a matrix that is so huge, I'm going to use a small matrix that has polynomials, and degree of each polynomial is going to be 256. So in that case, I just send two polynomials instead of sending, let's say, a matrix of the size of 512 by 512. So I don't have even that much of space to store them, but I can easily store two polynomials with the size of 256. So this is the reason behind using module-based learning with error. So when I say module-based learning with error, I'm just telling you to use polynomials instead of numbers for creating the matrix. Now we could use also ring learning with error, which means that what if we use just one polynomial, which is not a good idea in terms of then if that polynomial has any weaknesses, the security of your entire system relying on just one polynomial, which is not really good. So instead, we are using module learning with error. That means that we use multiple polynomials, not just one. And here you can see that the ring is ZQX divided by xn plus 1. What does this mean? It looks a bit fancy and tricky, but it's actually easy when I explain to you here. First of all, it means that every time a coefficient gets larger than 3328, we have to take the remainder after division by 3329. For example, let's say I am trying to create the coefficient for my polynomial. It is a1 x255 plus a2 x254 plus a255 x0. Now let's say I generate a1 and a1 is equals to 3330. A1 is greater than 3328. So we have to divide 3330 by 3328 and get the remainder. So I say remainder of the division of 3330 by 3328 equals to 2. So conclusion is that A1 is equals to 2. So you see, I don't let the coefficient to be greater than 3328. And what does this xn plus 1 means? So if you have two functions that you multiply them with each other, and each of them are of the degree 255 here, of course, the result going to be some a polynomial that has degree more than 256. So in that case, what we do, we say each time that we find, let's say again, fx multiplied by gx generates x to the power of 257, for example, plus x to 256 plus x to 255 and continue. So each time that I see x to 56, I'm going to replace this by minus 1. So this will be replaced by minus 1. And each time that I see x to 557, I replace it by minus x. The reason here is that here I have xn plus 1, and I just told you n is 256. So x to the power of 256 plus 1, if I put this equals to 0, so that's going to give me x to 56 is equals to minus 1. So it means that each time that I see 2x to the 56, I replace it by minus 1. Now, if I multiply two sides by x by x to 56 equals minus 1 multiplied by x. So conclusion is that x to 57 going to be replaced by minus x. So you see, we don't allow our polynomial to get a degree more than 255 here, or 256 to be more accurate. So here I just show you the whole process, the equation. So we have a polynomials matrix A. We multiply it by secret. This is our secret and plus a noise, and we get the public key here. Okay. Any question that you have? I'm gonna pause here for a minute to make sure everyone is clear. Let me check the time here.
Yeah, I have one question. So since I think the packet size is quite large, right? So any way to reduce the packet size because we transfer one packet to another packet, the speed is more important.
Yeah, so we have techniques. Yeah, Dan, that's a very good question. So we have a technique that is called encoding, which means that we try to break this packet into smaller chunks, and then we send it like that. And that's I'll talk about encoding and decoding later. But yeah, exactly. Before we send it on the internet on our communication channels, we can break it down to smaller packets, like a normal packet that we are sending, like that has the size of 256, for example. And that is just 1 byte, right? Because 1 byte can get up to 256. So we can break this into different bytes and then send the bytes. So that kind of like make it faster. Does that answer your question, or is it clear what I'm saying?
Yeah, thank you. But actually, my question is that, as you say, when we use the quantum shape algorithm, it will increase more than 1,000 bytes for each message, right?
Yeah. So you let me get back to that slide one more time. Actually, is here 1,024. I think it was.
That's what. Yeah.
I think I passed that. Yeah. So like here, for example, that we have, no, let me get back to the compare here. Okay.
Yeah, that's the one. Yeah.
So yeah, you see here, the size is 1,184 bytes.
Yeah, so every message equal add in 1,000 bytes. So it makes the transfer between from Bob to Alex much slower. So any way to reduce the latency?
No, because this is a fixed size, Dan.
Okay.
The size of the key, the public keys, always has to be 1,184. And the reason is that because if it varies so much, also is not good for some other type of compatibility issues. So we keep it 1,184 because because we can have a giant packet, right? Because we have usually runs and giants in the network. So even a packet that is up to 1,500, still it can be transferred within the internet, right? So I know your question is like how to still make it smaller, but we don't make it smaller
Yeah.
because if you make that smaller, then you lose information too.
Okay. Yeah.
Yeah. I mean, still that's a challenge. I know what you mean. Like, of course, it's not like an ideal solution right now, but still it justifies because like if the quantum computers can break the sensitive information, so at least we need a solution for that, right? Even if that solution is not ideal.
Yeah. Right. Okay.
Yeah, and of course that's been the reason also that it's going to take time for adaptation. You see, NIST also hasn't asked companies to transfer to post quantum like within the next months or so. They give them like 5 to 10 years. Some companies that have dealing with more sensitive information, for example, healthcare, they have to transfer by 2030, means that they have 4 years. But other companies that have less sensitive information, they can transfer until 2035. So they have almost 9 years. So in 9 years, a lot of things will happen too, anyway. And a lot of technology will also develop other stuff. So they are still keep optimizing this. Yeah, and you see, like AES itself also that was standardized in 2000. Of course, it wasn't a very fast solution, but right now it is very fast. I mean that time also wasn't bad, but I'm just saying like over time it's been keep improving and optimizing. A lot of research working on it. So when the adaptation becomes more widespread, I'm sure that more researcher will join also, and will offer more solution for the optimization and the speed.
Yeah. Thank you.
Yeah. So, so we have one function that we are using beside that three stage that I showed you right here. Here, the key generation, encapsulation, and decapsulation. Also, in this section that Alice decapsulate, also needs to use a function that is called FO transform. And this FO actually stands for Fujisaki Okamoto transform. What does it mean? It's like I'll show you later when we get a bit into depth of that. But it means that whenever Alice receives the ciphertext, it's gonna try to derive the key from that ciphertext, and will again encrypt it just in case, because we want to make sure that if there is an error in the channel, so attacker cannot realize that that key is not correct. It's just for tricking the attacker or making sure that the attacker get no information in case that decryption fails. So this kind of protects us against against a type of attack that is called adaptive chosen ciphertext attacks. And what does it mean if you have a decryption oracle? Decryption oracle, I mean, like, let's say someone is here and you can ask any question, you give them any ciphertext that you like, and they tell you what is the equivalent plain text for that. So I give C2 and this decryption oracle tell me that is X2. So you can ask any question that you like, but you cannot ask what is the plain text for that specific packet that you captured. Let's say you have Wireshark here and you capture the packet that is called CX. So you cannot ask this decryption oracle what is the plain text equivalent for this CX, but you can ask any other ciphertext and it will give you the answer. So if you can find the relationship between the ciphertext and plain text, then you might be able to find what is the plain text equivalent to this CX. That's gonna be, let's say, XX. So it means that it's not gonna give you the answer properly if you send the ciphertext and it was modified. So the receiver will not give you an error. Instead, it will send you a fake key. Don't worry about it. If it looks confusing, we're going to talk about it later. So here, again, ML-KEM 512 is actually gives you the security equivalent to AES 128. ML-KEM 768 gives you the security equivalent to 192, and ML-KEM 1024 equivalent to AES 256. And you already know these parameters that I talked about them before. So decryption can fail sometimes, which means that on very rare circumstance, Alice, my son, sends something to Bob, and Bob actually might not be able to recover the right key. Don't worry about why this exactly happens, because that can be a bit of a long conversation here. But just know that this happens very rarely, which means that the power of the rate of failure for the decryption going to be, for example, 2 to minus 138. This is actually like, for example, equivalent of being struck by an lightning 5 times in a row or 5 days in a row, which is very, very unlikely, but it still can happen. And even if that happens, no worries at all, because the receiver will ask again for the initializing channel one more time. So if Alice received the ciphertext using the private key, Alice can recover the message. Alice re-encrypts the message to get C prime, and will compare C prime with C. If C prime and C are equivalent, then Alice will get the key derivation function of M and of the message and the hash of the ciphertext. And finally, shared secret is generated. Now sender and receiver compares their key, and they see that key and key prime are equivalent. So both of them have the same key. This is a successful scenario. So now, what if something happens in middle? So you see Alice decrypts C, but noise causes a bit flip. So Alice see that the message is corrupted. It is called M error. So Alice will re-encrypt the message to get C prime and realize that C prime and C are not equal. So what Alice does is just getting the key derivation of a secret seed and the hash of C. Let me write this down. So this time Alice will get the KDF of the Z and the hash of C. And now this K prime, that is actually a fake key, will be shared. Receiver sends encrypted data using this fake key, which means that Alice is encrypted data with this fake key. And Bob cannot actually decrypt it because the key is fake. So they realize that the key was not successfully transferred. So you see, both of them could figure out that the key is not correct. I mean, the key is not shared correctly. I mean, I know that this can be a bit confusing. Like, if you have questions, please share with me. I'm going to pause here. Or you can read through it and then let me know if something doesn't make sense.
I don't have question on that, but do we have any like good library to implement it? Like, I don't know, in Python or in Go programming language or something.
Yeah, sure. I'm going to show you that like in some minutes.
Okay. Yeah, thanks.
Yeah, the whole idea that I want you to take away from this is that if something happened, like a noise happened in the communication, and Alice and Bob don't get the same key, in that case, they can realize it and they abort the session, and then they start to initiate the session again, right? And this is a very rare situation. But what if actually the ciphertext is modified, but not because of the noise, but because an adversary or attacker modify it? This brings us to the third scenario. So attacker intercept the ciphertext and changes a few bits. Now receivers decrypt the ciphertext that modified by adversary and recovers the message. And this message is garbage actually because it's been modified. And now Alice will re-encrypt the message with the key derivation function over Z and hash of ciphertext and realize that C prime and C are not equal. The check fails. So system generates or Alice generates a fake key and encrypt the message with this fake key. And again, Bob realized that the key was not correct. So both of them abort the session and start a new session. So again, if an adversary modifies the ciphertext, or if a noise happens in the channel and the ciphertext somehow get modified, both Alice and Bob will realize this and will abort the session and will start it over, which is again no problem. There are a couple of other things to have in mind. One of them is that there shouldn't be any floating point in our operation, which means that anytime that you multiply two numbers with each other or you divide two numbers with each other, you have to make sure that the result is not the floating point, which means that it should be a complete number. Here, if you divide x by y, you can get either the floor of that, or you can get the ceiling of that, or you can get the closest number to that. Let's say you are using this one. You are dividing two numbers and the result becomes 2.3. Since you are getting the floor of that, you replace this with 2. Let's say you are doing the division of two numbers and the result becomes 2.7. You get the ceiling of that and that becomes 3. Or can be closest number. For example, if the result is 2.6, the closest whole number to that is actually 3. So we replace this by 3. But why we care about it? Because this type of floating numbers can introduce random errors and they can create failures. So you have to avoid them. And also the other recommendation that NIST does is to remove all the temporary calculation. If you have done any calculation temporarily that you don't need it in the future, you have to get rid of them because that can create memory. For example, someone can extract the memory of your device and then they can find the key. Again, for the floating points, there are two issues. One of them, let's say your floating point is 0.50000001. And let's say once computer can round this up, the other computers can round it down. And that becomes a failure. And side channel attack can happen too. For example, if you have floating point operation, the amount of time that it can take to calculate also can vary, and it can help the attacker to get the noise or can find the decapsulation key itself. So again, the key takeaway from this slide is that make sure that whenever you do a division, the numbers are complete and whole. They are not floating point. And also get rid of any temporary memory that you have. And the output that your algorithm will generate is going to be 256 bit. That is great because then you can use these 256 bit for AES encryption, right? So both Alice and Bob can reach out to 256 bit. I'm going to pause again here one moment. So if you have question before I move forward. Question? Let me stop for 5 minutes. If you need to go around, drink water or take a short break, please do it. And let's continue at 2:41. But I'm still here. If you have questions, feel free to ask. So now for making sure that the ML-KEM works properly, we have to also understand like the inner working of this. Like there are going to be a lot of function being used there. And if you're specifically new to this field, don't get stuck too much to the detail. I'll share the slide with you later too, and you can read through it. And also I give you some other additional readings or watching videos. And if you have questions, you always can ask later, either on LinkedIn or on the YouTube that I'll post it later. But specifically, the functions that are interested here are the hash functions for different reasons. Of course, one of the reasons that we are using hash functions is to make sure that for the integrity of the information that we are sending over the channel. Let's say if you are sending the public key and anyone going to use that, you want to make sure that that public key is not modified, right? So you want to get the hash of that. And there are some other reasons too that I'm going to show you quite shortly why. So we can use SHA-3256, SHA-3512, and also we use Shake 128 and Shake 256. So of course, SHA-3 family gonna gives us the output of the fixed length, either 256 bit or 512 bits, and XOF function or extendable output function gonna gives us a variable output length, which means that you just give an input and you can ask for any length of the output that you like, which is very nice. Now here I provide a list of those functions. For example, we have function H, we have function J, function G, and XOF here. Let me use my pen so it focus better. So SHA-3256 is used for hashing of public key or hashing of the message. Already you know about it. Shake 256 here is used for domain separated hashing. What does it mean? I'm going to explain to you later, quite shortly. SHA-3512 is used for splitting the input into two 32-byte values. So let's say you have an input, it divided into two 32-byte, and one of them going to be your public seed that you're going to generate your matrix A from it. And one of them going to be the seed for the noise that you're going to extract the secret and also error from that later. And also this extendable function also going to be used for expanding the seed into matrix A. Why we do that? So you see this public seed is actually very small. So almost the size of that is 32 bytes. The size of this is 32 bytes. Now you can use the XOF function to expand this to the size that A requires, which is nice because you don't need to transfer a very huge matrix that has a lot of, I mean, it's a polynomial, but you have a lot of coefficient in that. Instead of that, you just transfer that small seed, and then the recipient can extract the matrix A from your seed. So yeah, just know that these are the four type of functions that are used for the ML-KEM. And here, the J function that I just explained to you here. Now let's see how we can use this J function. So remember, I told you whenever Alice tries to extract the shared key, and if realize that if key is equals to K is equals to K prime, then what Alice does is getting the key derivation function of the message and the hash of the ciphertext. But if key and the key prime are not the same, Alice will generate a fake key, and that will be done by J function. So that's going to be J over Z. This is a rejection salt that is concatenated with the hash of ciphertext. So now it will send that fake key. And again, attacker has no idea that that's a fake key. So that's great because we don't, it's like exactly when you go to a website and then you provide your username and password. And imagine that the website doesn't tell you either your username or password is wrong. So that's much better than telling them your username, your password is wrong. And then they know that username was correct. Kind of similar analogy here. Okay, let me go forward. Any question? Okay. Anytime you have question, just raise your hand. I'll stop there because I want it to be more interactive. Otherwise, it becomes boring for you. Yeah, and don't worry about this slide actually. Just for those of you who are familiar with the Ketchuk family, you know that we have a two process. First of all, of course, we absorb the seed and then we squeeze it and get more and more data. That's the same process. Let's not to get so deep into that. I wrote the process anyway here. This is the algorithm that is published on the ML-KEM standard. So you see, you get the initial seed, you absorb the seed with shake 128, and you squeeze as much as bite as you like. For conversion and compression also are used. For example, we need to convert our bits to bytes, and also we need to convert our bytes to bits. These are clear, like these are the pseudocode that you can use for converting from bits to bytes or for converting from bytes to bits. And also have this in mind that in ML-KEM documentation, we are dealing with little endian order, not big endian. What does it mean? It means that the order is actually received, meaning that the first bit in the sequence is the smallest value. So you remember, like in the conventional way of representing the bits, for example, if I say 101, you'll tell me that it is 5 here. This is 5 because this one is the highest value. But this is a big endian notation, big endian. Now if I type in the little endian, it's opposite, which means that 101 is that, but I didn't make a good example because again, the reverse of that would be again 5. So let me make another example for this. Let's put 100. This would be 4 in little endian and big endian, and 100 will be 1 in little endian because you have to reverse the order. You see, this becomes 001, and that gives us 1. So you see that that's how the architecture of your CPU can store it differently. Is it clear? If you have questions, let me know. I know sometimes this type of thing can be confusing. Just know that the bits are stored like in reversed order, and that's why we call it little endian. We also want to compress our data. The reason is that it's going to save us a lot of space. So we don't need to send very huge information. So we have a compression function that it takes your input. Here it takes our input. Let me see my pen here. Yeah. So it takes our input and it will transfer it to compress it to the to d divided by q multiplied by x. This is d is the amount of compression that you're doing. For example, d can be 10 or can be 4. If you choose 10 is a minor compression. If you choose 4, is going to be aggressive compression. I'm going to show you with one example how actually this is helpful. Let's say you have a number 1000 and you want to transfer this. This is your coefficient. Of course, 1000 is very big and it's going to take a lot of space. You know that you almost need 10 bits for transferring this number. So instead of that, we pass it through this compression algorithm. So it's going to be 2 to the power of d divided by q multiplied by x, that is 1000. Let's choose aggressive compression. So d going to be 4, 2 to the power of 4 going to be 16, divided by q. I told you that q is always 3329, multiplied by 1000 going to give us 4.8. Now, if I round this, it's going to give me 5. For transferring 5, I only need 4 bits. Instead of 10 bits, I can send it only for 4 bits. So you see, I save a lot of space. And now if I scale it back on the receiver side, I use this algorithm. That means Q divided by 2 to D multiplied by the compressed data. So 3329 divided by 16 multiplied by 5, that's going to be 1040.31. So that gives me 1040. These are not exactly equal, but they are close enough, so I don't care about it. Also, I compress it, and the decompressed data is not exactly the same, but still that is fine. So I don't mind about it because I could save a lot of space. It's like you send the video instead of making that, let's say, 4K, you're sending in a smaller resolution, but still the video is clear, so no problem. And now we have encoding too. Encoding means like, let's say you have the compression of 4. Now you have 256 coefficient, and each of them going to be represented by 4 bits. So in total, you have 1024 bits. So encoding will divide this into 128 bytes. So of course, that's now easy to be transferred over the channel, right? Because we know that we easily can represent each byte with 8 bits, so all the problems solved. So it's kind of like close to the question that Dan asked. I know that is exactly not the same, but you can encode the amount of data that you have, so you make them nice and tidy, and then you can send them over the channel. So here also shows like we use different bit depths for different object. For example, if you are dealing with public and private key, we'll use 12 bits, or if you are using ciphertext, we are using 10 to 11 bits. For ciphertext UV, we are using 4 or 5 bits. And for the message, we use 1 bit because our message is either 0 or 1 for each bit of the key that I'm saying. So if it's 0, we are sending 0. If it's 1, we are sending Q divided by 2 or 1665. Don't worry about the detail. What I want you to remember here is that you want to first compress your coefficient. Second of all, you want to make them tidy and clean so they can be transferred over the channel. That's it. And these are the functions for the byte encoding and byte decoding, the pseudocode that you can implement it in any language that you like. Okay, the next algorithm that we have is called the sample NTT. Is just used to generate the matrix A. So first of all, we provide the to the squeeze process 3 bytes, and now it splits this 24 bits into two 12 bits integers. And since Q is 3329 and 12-bit numbers can go up to 4095, so always we have to make sure that the numbers that we are generating here is smaller than Q. Otherwise, we have to repeat this process again and again because we are trying to find the coefficients, right? And if coefficient is more than 3328, we have to make sure that we do the modulo operation on it. So at the end, the result of this sample NTT going to be an array of 256 coefficients that are uniformly distributed. And here's the pseudocode of that, and you can implement it again. So you provide the 32-byte seed, and then the coefficient of the NTT will be generated based on that. Okay. Now also I talked about error and also the secret, how we're going to generate those. These are very easy and very interesting. This is called the center binomial distribution. For those of you who know a bit of the statistics, so center binomial distribution is looking like this. So here you see 0 is most of the time is repeated here. Then we have 1 or -1. And here we have eta plus or minus eta. That can be 2 and minus 2. Here plus 1, plus 2, minus 1, and let's say minus 2. So the process is very actually nice. You see, we take 2 eta or 2 times eta bits from a random string. So let's say you have a random string that gonna gives you 6 bits. Those 6 bits gonna be, let's say, 1 1 0 0 1 0. Yeah, that's it. Now we divide it into 2 parts, each of them 3 bits. So let's say this part will be called X, and this part will be called Y. Now we subtract X and Y. We subtract X and Y, and we see what is the result. Let's say your X is 1 1 0, and your Y is 1 0 0. So it's going to be 2 minus 1. The result will be 1. So your random numbers for error will be 1. So if you have a matrix of the size 2 by 1, your first number going to be 1. And let's say your second number is, again, by the subtraction of X and Y, going to gives us 3. So your second number is 3. So this can be, for example, my error vector, or can be my secret vector. So here we have to generate 2 vectors, error vector and secret vector. So if I have my matrix A, that is 2 by 2, multiplied by secret, let's say my secret is 1 and 3, plus the error terms, let's say my error terms here minus 1 and 2. So now I can easily find the public key. And I can share this public key with anyone who wants to send a message to me. And again, this is the pseudo code for that. You can walk through it and see how exactly it's working and I explained the logic behind it. So you can see it X minus 1, and again, you get the final value. So yeah, to summarize this part, we have a sample entity, we have sample poly, central binomial distribution. This sample entity is used for finding the coefficient of your matrix A. And this sample poly CBC is used for creating the secret vector and also noise vector. That's it. Any question? Now we get to a very interesting part of the ML-KEM. And that is like if I have 2, let's say, matrix, or let's say I have 2 polynomial, I'm going to call them fx. I'm going to call them fx and gx. And each of them are of the degree 256. Let's say this is, again, x 255 plus 2x 254 plus x0. And here also is, let's say, 10x255 plus 3x254 plus 90x0. How you multiply these two together? If you just go with the starting to multiply 1 by 1, actually that becomes a very slow process. And this is not convenient at all for using that, because we need millisecond operation. How can you do it in millisecond? So instead, we're going to take them to a different domain. We're going to transfer this polynomial to an NTT domain that I'm going to explain to you what is this NTT domain. They're going to make my operation much faster. And let's see how that's possible. And I delete here, yes. Let me go directly to the example and then I show you. So these are the process. It's called NTT. a function, and also we have the reverse on the other side. But how that works, let's look at it here. So this is the process that we are interested in. You see, first we have to set I equals to 1, and the length variable will be 128. And as long as length is greater than 2, we'll continue the for loop here. So we put 0 into the start, and we raise the eta here to the power of bit rev 7. That I'm going to explain to you what is that, modulo q, and we keep incrementing I as long as length is greater than 2. And also we have another variable that is called j, and that's going to help us to find the transferred polynomial. It's confusing right now, yes, but with an example, everything will be clear. Let's see. Here's my example. Let's say you have an polynomial f that is like this, 1 plus 2x plus 3x2 plus 4x3. So you know that f0 here is 1, f1 is 2, f2 is 3, and f4 is 4. Now I have to do a reversal. What I mean, I just means like I swap the places of bits. For example, if I have 0, 0, the swap the places again is going to be 0, 0. If I have 0 and 1 and I swap the place of these two, is going to be 1, 0. 1, 0 becomes 0 and 1, and 1, 1 stays 1, 1. Wait for it, and then you understand why I do all this stuff. So first length is equals to, let me bring my pen. And also I'm going to delete here to make it clean. Okay. So I know that here n is 4 because my polynomial is of degree 4. So length is going to be n divided by 2, which means that 4 divided by 2, that is 2. Now I have to find zeta. So I is equals to 1. I said the first stage I is equals to 1. And what is the bit rev of 1? You see which one is 1 here? 1. This is bit rev of 0, bit rev of 1, bit rev of 2, bit rev of 3. So let me put it here. This is bit rev of 0, bit rev of 1, bit rev of 2, and bit rev of 3. It means like reversal of the bits. That's what it means really. So what is bit rev 1? You see here is 2. So okay, here I set this to 2, and I need to raise eta to the power of 2. Eta is already 4, so 4 to the power of 2 becomes 16. Great. Now I continue. I set j to 0, and now I have to use that equation. Let me get back to the equation, to the previous page. Right now I am here. Let me delete everything. Here. You see right now I'm here. For j equals to 0, I have to multiply zeta. Sorry, I said eta. I mean zeta. I have to multiply zeta by f of j plus length. What is length? Length is 2. So j is also 0. So I have to multiply zeta by f of 2. Let's go to the next slide. 16 multiplied by f of 2, and here I said f of 2 is 3. 16 by 3 going to be 48, and I do everything modulo q. Here I choose q to be small just for the sake of simplicity. So if you do the remainder of this, you get the result to be 14. Now that I have calculated t, I need to find f0 and f2. f2 here, f2 is equals to fj minus t. And we know that j is 0, so it means that f0 minus t. So here f0, that is 1, minus t, that is 14, becomes minus 13, so the result is going to be 4. What about f0? f0 is going to be f0 plus t. f0 is 1, plus 14 gonna be 15. So far I could find f hat 2 and f hat 0. And you see here, you see the result. I could find f hat 2, this one, and I found this one. I still need these two. So I do the same for the next two indexes, except that this time I set j equals to 1. So 16 multiplied by f3 gonna be 16 multiplied by 4, gonna be 13. And then f3 is gonna be 2 minus 13, and f1 gonna be 2 plus 13. So that's gonna give me 6 and 15. Now I can replace this in my matrix. Now I create two blocks. With the first two, I create one block. I call it 15 plus 15x block 1. And block 2 gonna be 4 and 6, 4 plus 6, 6. And now I can do the same for the g function. And now I can multiply them block by block. And this makes the computation much, much faster. If you don't understand it after the seminar, please go and walk through this algorithm with the toy example that I provided. And if it still doesn't make sense, let me know and we can discuss it more. But just know that, again, this is equivalent to the Fourier transform, but this time for integers. That's it. So yeah, let me skip here. So this becomes, again, much faster operation that we can use it. Again, if you have two functions, you transfer them to the entity domain, and then you multiply them coordinate-wise. Okay, and this is the last part of the presentation. If you didn't get anything of this presentation and you only get this part, you're totally good and no problem at all. You are really capable of helping your company also to move towards the PQC as long as you understand this part correctly. So what we need here for creating, again, the public key, we need a matrix A, we need a secret vector, and also we need an error vector. So T and P actually becomes our encryption key. T and P. This is actually the one that is used for generating A matrix. That I told you, this is the seed for generating matrix A. And S is your secret key. Now you can go through this algorithm to just multiply this multiplication and addition. Next part. We are getting to Bob's side. So that was Alice's side. Now is on the Bob side. So Alice needs to do a couple of things. First of all, Alice needs to figure. Bob. Again, I said Alice. So Bob needs to figure out a couple of things. First of all, what is the message that Bob is trying to transmit? When I say message, I actually mean the key that Bob is trying to send to Alice. So this is a 256 bits key. Let's say it's 1011011. 0. And this is the size of this is 256. This is my message. Or actually is my key that I try to send from Bob to Alice. Also, Bob needs to find the vector y that is actually a vector of size k by 1 of polynomials, and also need to generate a noise vector. So that is going to be generated from that 32-byte seed. Now, what Bob needs to do, again, I write here Bob so I don't forget. So need to calculate two equations. One of them is U and one of them is V. U is equals to A transpose. You already know what is A matrix, multiplied by Y. That Y is just a vector of that is driven from the center binomial, plus an error 1. This is an error that Bob find the vector. And V gonna be T transpose and plus E2 plus message that is hidden into this Q, which means that if M is 0, let me clear here. So here, if m is 0, so this is going to be 0. And if m is 1, this is going to be mapped to 3328 divided by 2. So that's just for hiding your key inside this equation. That's it. So now we compress C, we compress U and DU. That gives us C1, and we compress V and DV. That's going to give us C2. Let me pause here. Okay, please think about it one moment and let me know if you don't understand it. This is really the most important part of the entire conversation. This is all the operation that Bob needs to do. So I want you to just focus on this part here on this site. Just focus on this. So Bob only needs to find these two equations. And now Bob can figure out what is the ciphertext that can send to Alice. Any question? And you know what is this T? T is the one that we calculated in the previous section, and that was T is equals to AS plus E. That's a public key that Alice generated before. So when Alice received the message, needs to make sure that the ciphertext is correct and the key is correct. For doing that, so first of all, decompress C1 and C2, and finally calculates V prime minus V prime, that is the decompression of C2, minus S transposed U prime. And Alice successfully can figure out what is the message or what is the key. Any question? Anyway, I can get back to this after we finish quite shortly. So this is going to be a summary of the size again. For k equals 3, encapsulation key is 1184. The encapsulation key or private key is 2400, and the shared key is going to be 32 byte. That is, of course, 256 bits that can be used for AES or CHA-20. Let me skip this part. You can read that. Kind of similar to whatever I discussed so far. The 3 algorithms that we need: keygen by Alice, encapsulation by Bob, and decapsulation again by Alice. And these are the pseudocode of the algorithm that I just show you. And also at the beginning, we have to make sure that first of all, the numbers that we are generating for coefficient are between 0 to 3328. Second of all, we want to make sure that the size of the keys should be 1184 bytes for consistency. And also we want to check the hash of the public key to make sure that the public key hasn't been modified. I talked about it in the past. If you need equivalent security of 128, use ML-KEM 512. And this is recommended by AES 768 because this is like a trade-off between security and performance. And this table that I showed you at the beginning, again, I provide the same here. So now you should understand what is N, what is Q, that is the modulus, the K, that is the size of the matrix, eta 1 and eta 2, that is the size of the error vectors that you generate, which means that your error number is going to be between -3 and 3, or here between -2 and 2. And these are that used for compression of the polynomials or coefficients of the polynomials. Yeah, that's it. I'm going to show you quick Python demonstration too. Let me stop sharing here.
Excuse me, Elias, before you stop sharing, what is the NTT algorithm for? It just for compression or?
No, the NTT is just again is an equivalent of Fourier transform. You know what it again what the whole concept, the whole thing that we try to achieve here to make sure that we can multiply the polynomials very fast. Let's say again you have a very large polynomials and you want to multiply that polynomials with another polynomials that is also very large, that's going to take you a very long time. Instead, we want to transfer it to a domain that we can quickly multiply them, right?
Okay.
Let me
Yeah.
explain that again. I stop after this code and then I'll show you with example.
Okay.
Yeah, let me just, do you see still my screen?
Yes.
Which screen you see? Is it the PowerPoint or my
It's the
browser?
PowerPoint. The
Okay.
PowerPoint.
Yes. So let me see here. Mm. Okay, now you can see Collabs, right? Google
Yes.
Colab.
Yes.
Okay. Yeah. So here I took this code from the Python official website. So it's very straightforward. I just need to install the Kyber Py and PyCryptodome. And after I install these two packages, I can quickly get all these keys and that by either Kyber or ML-KEM. You see, I remember I told you ML-KEM is actually this Kyber that is being adapted by NIST. They have a little bit of subtle differences because the original Kyber submission been optimized and that was standardized under the name of ML-KEM. So here you can also do the same for generating your keys by Kyber. But of course, since we are interested in the standard, I go to the second part that is generating the keys by ML-KEM. So let me walk you through this function. You see, first of all, I have to call this, that is ML-KEM 512. You can call any of these three class that you like, ML7 or 768 or 1024. And then you call this ML-KEM512.keygen that's going to generate the keys. And you see there are two keys here. What are these keys? Encryption keys and decryption key. Now, this part is done by Bob that is generating the ciphertext and generating the shared keys. And finally, Alice will do the decapsulation by using the private key and the ciphertext. It will generate the shared key. Now this is the shared key that I generated. Now I can use this key for using AES. You see in the second block of code, I'm using AES with the key that I transferred by ML-KEM, and I'm using AES GCM mode. And I can successfully encrypt my encrypt my plain text. My plain text or my message is this is post-quantum secured message, and I can successfully encrypt it and becomes this ciphertext. So I shared this with you so you can have it too. Any question here? So this is the whole process that I explained to you. Of course, this is not the final code because you have to make sure that you consider the hardware attacks and also other optimization techniques too. But just shows you the entire process that really what is happening in Kyber. The whole process again is just three function: keygen, encapsulation, and decapsulation. Okay, let me stop sharing here and share the the code with you. Here. Yeah, here's the slide. I sent the slide also in the chat, so you can download it. And also the key for the okay, I sent both of them so you can download it. Yeah, so now let's get back to the question and explain whatever that was unclear. So first of all, Maida, you asked about the this process for generation of the for NTT. Let me get back to it. Okay, let me explain here. That is a clean screen. So again, let's say you have two functions. It's going to be fx. Both of them are polynomials of degree 256. So let's say this is a0 x 255 plus a1 x 254 plus this plus a255 x0. And the second one is g of x. That is, say, let's say this time b. Let's use b coefficient. b0 x255 plus b1 x254 plus b255 x0. Now, if you want to multiply these two together, how you multiply them? You have to do this. You have to write a0 x255 plus a1. This one a255 x0 multiplied by the second function. So now you have to first multiply this by all these 256 elements here, which means that you have to do a0 x255 multiplied by b0 x255 plus b1 x254 plus b255 x0. And you have to continue this again for a1, right? a1 x254 multiply again by the entire of this function. You see how big is this? Like you have to do it. How many times you have to do it? You have to do it 256 times. And each time, how many calculation? For example, for the first one, you have to do 256 multiplication here. So this kind of takes me 256 multiplication. Here again, it's going to takes me 256 multiplication. So can you tell me in total how many multiplication is going to be? So in total is going to be 256 multiplied by 256 multiplication. That is equivalent to 2 by 8 by 2 by 8. That's going to be 2 to the power of 16. That's going to be 65,536. So 65,000 multiplication, isn't it so big? So instead of doing that, I can transfer them to a domain that is called the NTT domain. So let me remove here. And now we see how faster it can become. I can do this entire process in 128 operation. So yeah, let me take here as well. So first I transfer the domain of the fx. So I transfer the domain and fx becomes something like this. A0 x255 plus A1 x254, and then plus, of course, I have to do after NTT domain, NTT domain. So this is not going to be A0, it's going to be A prime, A1, A2 prime, plus A2, A3 prime, x252, multiple plus here A prime 254, x1 plus A prime 255, x0. Here x1 it is, sorry, not x prime. So now I do the same for G, and G becomes B0 prime x255 plus B1 prime x254 plus B0, no, B0 again, B2 prime x253 plus B30 x252. Yeah, almost there. P B254 P prime x1 plus B255 x0. Now what I do, that I did the entity transfer for both of them, I just need to multiply this together, these blocks together, which means that I just do a multiplication of these two blocks, and continue until the last block. So you see, instead of that huge multiplication, I just do block multiplication. That makes it actually much faster. So you can see that the total number of multiplication is 128. This is the first multiplication. This is the second multiplication. And this is the last multiplication. That is the number 128. Does it make sense or no?
Yes, thank you.
Yeah. So anyway, even if for anyone is not clear, just know that by converting these functions to a different domain, we make our multiplication much faster. But of course, for implementation, you don't need to worry about it. For those of you who are developer and want to just implement it in Python or C or any other language, already the modules are there. You just write one line of code. Even you don't need to mention anything about it. By default, it will do it for you. So just something to have in mind that it's doing this. Yeah. Next question. Okay, I am still waiting for next question. Yeah, usually not question is can be two signs. One is that it was so clear that everyone got it. And the other that hopefully is not the case is that nobody got it. Okay, so I stop here. You are free to leave, please. I see a chat here. If you have any question, please again feel free to ask either in LinkedIn. For those of you we see each other in the class, we can discuss it in the class, or in the future seminars, or in YouTube. You want to ask for those who that we are not in direct contact, or any way that you like. Just let me know. And yeah. Yo, it's getting bedtime, Eric. Thank you so much for coming. Yeah, I know you're joining from Europe and it's already very late. Yeah, really appreciate everyone who joined today. If you have any other topic in mind that want to discuss it, let me know. Thank you, Andre. And thank you, Ankit. Thank you, Monk. Yes, thank you, Maida. Yeah, I'm gonna stop sharing here anyway. And recording. Yes.